Dr. Mostafizur Rahman. So I'm going to read out his brief biography. Dr. Mostafizur Rahman is a research scientist at IBM Research Lab in Quantum Division. He earned his PhD in quantum computing and his MS research in statistical signal processing from IIT Kharagpur. During his PhD, he received the prestigious Prime Minister's Research Fellowship and commendation from the Ministry of Education for his doctoral research work. His research focuses on designing novel quantum algorithms for various linear algebraic subroutines in signal processing, machine learning, and quantum simulation. Dr. Rahman has co-authored multiple articles in IEEE Transactions, Nature journals, international conferences, and holds several international patents. He's a senior member and an invited visiting scientist at RIKEN, Japan. He is a contributor to IBM's Qiskit software and India's quantum ecosystem initiative, including national quantum missions. We are honored to have you here, and it's over to you.
Yeah, thanks. Thank you, sir. Thanks a lot for this elaborated introduction. And it's really an honor to get an opportunity to interact with the all the participants, especially they are the real contributors of our National Quantum Mission, and it's a great opportunity to interact with them through this MNIT program for the CICT QT-06 course. So I was also part of QT-1, QT-2, QT-3, QT-5, and QT-6. As Professor Pillai sir told me, if I can take 1 or 2 days. So it's really an honor. So thanks a lot. So shall I wait for a couple of minutes, or all the participants already?
I mean, we can start, but before that, I just want you to know that the participants are already familiar with the basics of communication system theory. So they have last week, they have studied about normal communication theory, information theory. So they are familiar. They also studied polarization optics and so on. So basically, probably in your topics, they don't need the polarization optics part. Definitely, they will need the information theory part as a prerequisite, I guess.
Yeah. So I probably today I'll be covering the Shannon quantum information theory part. So
Okay.
and it won't cover any classical part. Also, there might be little bit similarity with other QT, like probably QT2 or so, where I gave some introduction of quantum communication. So purely it is quantum. And tomorrow I'll cover various noisy quantum channel and no cloning theorem. Actually, there is no crystal clean specification of the syllabus in the quantum part of the quantum communication, right? So there are lots of things in the syllabus, and it's very difficult to, specifically if it is topic wise, right? Now the title is fine, like it's a Shannon theory, but Shannon theory itself can be a book, can be many articles, many things. So it's really a bit difficult, but of course, with a combination of, I'll keep about 30-40% of undergraduate level and about 60% of postgraduate level content, so that because most of the participants are faculty members from various institutions, so they can actually, when they will be teaching, they can actually think based on the student capacity and all what information should be given.
Right.
And
So,
notes and all I'll be sharing through Professor Pillai sir. So maybe you can share among them. Yeah.
One more thing is around 3 o'clock, I request you to take 5 minutes break so that we can split the streams into 2 sessions for today, for today's event, basically. And secondly, at 3 o'clock, my other coordinator, Dr. Kavita Lalwani, will join, and she will take it over. And in between, if you have any help you need, our EICT Academy technical team is already there.
I see. Sure.
And if you want, generally the participants are interacting through the chat window. So do you want our team to
I am familiar with this. So I have taken, this is 5th course I'm taking. So thank you so much. So I'll be taking care of all these things, sir. So no worry.
All right. Okay. Thanks. Thanks a lot. You may begin your talk. Thank you
so
very much.
My screen is visible, right, sir?
Yeah, screen is visible.
Right. Yeah, thanks a lot. Yeah. So today, let's start. And I'll be taking 1 hour plus 1 hour, 2 hour sessions with the 5 minutes break in between on Shannon quantum information theory. So please allow me just a minute for the setup if it does not work. Just a minute. Just 1 minute, please. Sometimes this digital board creates issues and all. Yes, now it's working. Sorry for the interruption. So today we'll be covering the portion on Shannon quantum information. And reference, there are basically two reference book. One is the Quantum Computing and Quantum Information by Nelson and Chuang. And the second book is by Quantum Information Theory. Theory by Mark M. Wild. So we'll gently start the subject. I'm assuming that some of the scholars and some of the faculty members might be new. And my approach, although quantum communication has various way of defining quantum communication, but today and tomorrow we'll be focusing the information part of the quantum communication, specifically quantum information part. And because I have a background from the quantum computing part, specifically from IBM, so we'll try to connect both ways, like the quantum computing, quantum communication that is part of quantum communication or quantum information that is part of quantum computing itself. Specifically, how it is related with quantum noise, various hardware noise, and various quantum channel, how they actually implicate, how they interfere the quantum information, the information that we are interested. So those part actually we'll start with that. And then tomorrow, the second part here, mostly we take care of the superposition and interference phenomena of quantum mechanics that is related to quantum communication and its implication in computing. And tomorrow we'll focus various entangled state, composite quantum system and entangled state and their implications on the security. Specifically tomorrow we'll focus on no cloning theorem. And this is basically the underlying principle or heart or core of the quantum security or quantum cryptography. So tomorrow we'll focus this part, but today we'll start with the various quantum communication part from the quantum computing knowledge, the quantum computing course that we have taken QT-05 from that part, right? So we are dividing the lectures of today into two parts. One is the noiseless quantum theory. Noiseless quantum theory, and after that we'll slowly go towards the noisy quantum theory in the second part, and we'll be defining various representation, mathematical representation for understanding the noisy quantum system. Specifically, we'll start with the density matrix approach. So the way the information flow will be there in this particular 2 hours lecture is a bit different than the way that if you want to compare with the digital communication with communication, that is not the way, but better the first part you can directly relate with what quantum computing knowledge you have acquired with that to the quantum information part. Okay, so the first part is in the noiseless quantum theory, there are 3 main steps, right? Even if we see various the quantum algorithms, in fact, so what are the basic steps? One is the state preparation, right? So you initialize with a quantum state Kate psi. So I'm not defining any basics of what is Kate psi and all. So this is already covered in the previous QTs, but we look those things from the information theory way, not directly from the way it is taught as a linear algebraic language, but from the information theory part wise. So you start with the quantum state Kate psi, and then we did evolution, like the time evolution part, right? And we get an evolved state, right? The evolved state is u times Kate psi, which is the product of the vector times the matrix, right? The matrix is the unitary matrix U. So this is our initial state. This is our time evolution. Following, if it is isolated system, so it will follow e to the power IHT form coming from the Schrodinger time evolution equations, right? And if it is not an isolated form, so if it is a noisy form, later tomorrow we'll see the master equation form. Then we reach to a state which is an evolved state, right? U times the state psi, which is you can call as phi. This is the state. And then you have done the measurement and you get the classical result output, right? After the measurement. So this is the general steps of any quantum algorithm, right? A general noiseless qubit can be hence represented as Kate psi equals to alpha Kate 0 plus beta Kate 1. And if you see some of the previous QT series, I have shown in detail, and other experts probably, they have also shown that how you represent a quantum state vector as like a linear combination of, or the superposition of the basis states, computational basis states Kate 0 and Kate 1. They are orthonormal basis, right? And you can represent any quantum state with this, with the constraints that alpha and beta are certain complex number and they are normalized. That means alpha squared plus beta squared equals to 1. This is what we know from our already existing knowledge, right? So alpha and beta, these two particular coefficients, they are called the probability amplitudes. Not the probability, called the probability amplitudes. Not probability. So they are not probabilities themselves, but they allow us to compute the probabilities through quantum measurement, right? So by quantum measurement, we will see that these coefficients will help us to compute the alpha square and beta square, which are the probability quantities, right? And I'll come slowly towards that point. Now, if you have a general state, like with multiple bases, say for example, Kate psi equals to many combinations of the orthonormal basis ket with certain coefficients alpha I for many such I, right? So if this is my superposition state for many computational basis, right, ket I, then eventually the probability sum alpha square will be equals to 1. This is the normalization constant following the Born rule. Right? So this is a probabilistic, basically it gives the probabilistic interpretation, and it will speak more on this during the quantum measurement part. So instead of the classical or the Boolean logic, so basically 0 and 1, the classical information theory that is taught just in this quantum communication part, in the digital communication and all those parts. So these are basically bits which follows the Boolean algebra, right? And because Boolean algebra does not allow to represent information in superposition state, it does not allow information to represent in superposition states. Hence, we cannot follow the Boolean algebra for the quantum computing or the quantum technology or the quantum communications, right? So we instead need everything in terms of the quantum state representation in terms of the linear algebra. So linear algebra will allow us to create the superposition state, because from the definition of the vector space, that means if you have one vector v, another vector u and v, they belongs to some vector space or the set of bigger vectors v, and there is another set f, then you can do alpha u plus beta v, which should belongs to the vector space capital V, subject to alpha and beta belongs to the scalar field f. So this is we are getting from the definition of the vector space, right? So it is allowing the superposition. So this is the natural language. So hence this becomes the natural language for describing quantum information, right? That's why information goes from 0 to ket0 is one alternative, and another alternative 1 goes to ket1, but they are not necessarily the same thing. These are the scalar Boolean logics 0 and 1. Here we have the vector quantities ket0, which is basically 1, 0, and this is basically equals to 0, 1, right? And we have multiple times we have defined this ket0, ket1, but today we'll be inspecting them from an information theory way, not the linear algebraic calculation that we have seen in the previous QT series, right? So now basically, as we can represent any vector, say R vector as a like combination of, say, this is your I hat and this is your J hat, right? If these two are I and J are orthonormal basis sets, then any vector R you can represent as, say, this is your A amount of I hat plus B amount of J hat, right? This is the way we learned from our childhood to represent vectors, right? So similarly, you represent it instead of any R, you represent a particular state vector ket psi, which is just simply a vector, normalized vector, as a times ket0 plus b times ket1. And here 0 and 1 are the orthonormal basis. That means this is your 0, ket0, and this is your ket1. This is simple Cartesian coordinate representations, right? And this is your quantum state ket psi. So now, if this is my vector, and my representation is alpha amount of ket0 plus beta amount of ket1, right? That is the state ket psi. If this way I want to represent, right? And this is basically, even if I look at this is my 0, 0 origin, so this point will be 1, 0, x coordinate is 1 unit, y coordinate is 0, and here it is 0, 1. So by direct inspection, we can see this particular point, this particular, if I call this as a vector and this as a vector, so this ket0 is by definition, if this is my ket0, so this is basically 1, 0, and this particular vector is basically 0, 1. And in the circular representation, basically circular coordinate system, you can simply, or spherical coordinate system with radius equals to 1 unit circle. So this is your this is your 0, 1, right? And that is what we call ket0 and ket1, and any quantum information, basically ket psi, we represent with some amount of ket0, alpha ket0, and some amount of ket1, beta ket1, right? This is how we represent the information on the circular coordinate system.
Now there is a special coordinate representation. I'm not going details or anything. I'm just giving the definition, the block sphere representation. It's a three-dimensional representation. Here, this is Ket0 and this is Ket1. And by simply looking at this, you will say, okay, this is 180 degree. But the representation of the definition of block sphere is as such that opposite pole represents 90 degree orthogonality. Okay. And specifically the norm is 1. That means 0, 1 if it is Ket1. So we can easily see the norm of this vector equals to 1, right? Square root of 0 square plus 1 square equals to 1. Or similarly for Ket0, the norm is 1. So this is basically orthogonal as well as normalized. So these are orthogonal. Ket0 and Ket1 are orthogonal to each other, right? So they are orthogonal as well as their norm equals to 1. So that's why they are orthonormal basis vectors, right? Orthonormal basis vector. So this is how the basic fundamental information we represent on a quantum system. And now the system is whether it can be Cartesian coordinate system, it can be circular coordinate system, it can be block sphere coordinate system, right? Various coordinate system we can think of. Now let us also, as I just told that this is a quantum state psi, and if I represent in a three-dimensional way, so there are two additional angles. One is the basically azimuthal angle, and there is elevation angle, right? Theta and phi. So considering one of them and the other we can say as a global phase, we can also represent that alpha equals to your say R0 e to the power I omega 0. This is your alpha. And suppose beta equals to, we can represent as R1 e to the power I omega 1. And instantly, we can also represent the quantum state as R0 Ket0 plus R1 e to the power I omega 1 minus omega 0, right? I have just taken the common, right? Just certain like you could represent as a alpha Ket0 plus beta Ket1, and then you put the value of alpha and beta and then take like e to the power omega 0 common or something. Then you can directly reduce in a 2-3 steps to this particular state. So this state, they are equivalent to the state alpha Ket0 plus beta Ket1, right? Now we'll see if you directly measure, you will be getting, if you directly measure to the state 0, how to measure by mathematical projection, I'll come. So you will be getting alpha square, here you will be getting beta square, right? Similarly, even if you do the measurement here and here, right, you will be getting information about R0 and R1, but not the information about this omega 1 minus omega 2, because by doing the measurement and taking the modulus, this part will not come into picture, but that's why it's called a global phase part. But actually we can manipulate this part because alpha and beta are the complex quantity, right? So by means complex quantity, there is a angle, right? So there is a basically a modulus part. There is a modulus part and there is an angle part, right? So that angle part, if you do the direct measurement of individual basis state 0 and 1, we cannot recover. So there is a specialized technique called quantum phase estimation or phase kickbacks technique. So I'm not covering here today. That's part of quantum computing. There is way to recover the phase of a particular quantum state or the phase of a eigenvalue of a quantum operator. So those things are there. So that is a different part. But this is also how we can represent the quantum information. So the basic difference is that earlier. So let us, if somebody asks you that what is the basic difference between the classical information? Yeah, it is relative phase. So I'm also seeing the chat question. So relative phase W1 minus W2, and phase you can always represent by angles, right? So either you can put the phase in front of both the Ket0 and Ket1, or you can take like one part out as your like 0 and other part as a relative phase, both ways. Now earlier we represented information as a set 0 and 1, right? So whatever message you transmit from your transmitter to receiver, right, TX to RX, so all the receivers ultimately in the binary form, they are either 1, 0, 0, something, some message is there, right? And if there is some errors in a particular bit, 0 or 1, so there are techniques like both in the channel encoding, the source encoding, as well as detections. There are various error correcting techniques in the classical genre, right? But in quantum, now our information is taking help of two basis vector Kt0 and Kt1. Also, their probability amplitudes alpha and beta. And even if there is no noise in the system, this uncertainty in the classical bits is coming due to the noise part, right? Suppose you receive certain data stream and that is transmitted, right? And there is no, even in fact, if the system is perfectly fine, there is no noise, no channel interference, no hardware noise, nothing. So you can perfectly reconstruct them, right? Without any additional intelligence. But here itself, your information Kt psi, that is basically containing alpha and beta, and by a single measurement, you cannot say whether it is belongs to the state Kt0 and Kt1. Hence, your information is encoded in alpha and beta, right, which are probabilistic quantities. And that largely depends on the various noisy models we'll see, right? There is somebody else asking, won't it be alpha square? Yeah, I mean, when I am representing alpha and beta, always I mean probability amplitude, okay? Probability amplitude is not probability. The probabilities are alpha square, beta square, okay? I will see, we won't define why probability is alpha and beta square. We'll come to this via quantum measurement, right? So please keep patience for some time and in detail, we'll see what measurement means. Okay, so now let's see, let's calculate probability amplitudes alpha and beta, okay? So if this is a vector and this is Kt0 and this is Kt1, right? And this is your Kt psi. So now we don't know what is the coefficients that is sitting in front of alpha and in front of beta, right? So what mathematically we do a projection of this vector to this axis, right, in order to get alpha, and we'll do a projections to this axis in order to get beta, right? That is what we do, right? So if we do that, right? So we'll be getting alpha as a constant part, it will come outside, and 0 inner product 0 plus beta 0 inner product 1. So this part will be dot product between the vector with the same vector, unit vector, equals to 1. And this, because 0 and 1 are orthonormal basis vectors, so it is the dot product, because they are orthonormal basis vectors, so dot product equals to 0. So beta into 0, so you will be getting alpha here, right? And if you do the projection similarly on this particular basis, right, and on the basis 1, we'll be getting beta, right? Similarly, just by doing your Kt1 alpha 0 plus beta 1. So, sorry. Right. So by simply multiplications, you can get it is equals to beta. Now, if I do psi times psi, that means I do the projections of a vector to itself. Then what we'll be getting, just simply, this is basically equals to your alpha star Kt0 plus beta star Kt1 multiplied with alpha 0 plus beta 1, that is equals to alpha squared plus beta squared mod, right? And this is we know, because if 0 and 1 are the only possible state for the state psi, then this is obviously the sum of the square will be equals to 1, right? So also this is related to the Euclidean norm. Euclidean norm is given by psi 2 norm equals to square root of psi and psi, that is equals to square root of 1, that is equals to 1, right? Now, 0 and 1, Ket 0 and Ket 1. Here we'll be calling them as are called computational basis states or computational basis vectors. Computational basis vectors. Now, not always will represent the information as a combination of this Ket 0 and Ket 1. That means just what we have learned that alpha, we can represent a state vector in terms of alpha Ket 0 plus beta Ket 1. This is for simplicity because how we define this Ket 0 and Ket 1 using certain quantum hardware. If it is, for example, superconducting hardware, then you have this ground state and the first excited state like equals to Ket 1, Ket 0 as a ground state, Ket 1 as a first excited state. Similarly, just initially, the course conductor organizers told me that experts already covered the polarizations and those things. And there you must have seen that the horizontal polarizations, how they define as a Ket 0 and the vertical polarizations and Ket 1, right? But this is not the way, just we always have to represent our quantum information. But there are other bases also. Further, we can also represent informations by the basis Flask Ket that is equals to the superposition of 0 plus 1, 0 plus 1 by square root 2, that is 1, 1 state, right? And the minus state, that is 1 by square root 2, 1 minus 1. So that means I can also represent any quantum state or the quantum information as some gamma amounts of plus state plus delta, some coefficient of minus state, right? What is gamma and delta? So we'll see later. This is alpha plus beta by square root 2, and this is alpha minus beta by square root 2. We'll check later. So this is another way to represent our state, right? Now here also, so how this plus state and minus states looks like. So in the blosphere, we have seen this is Ket 0 and this is Ket 1, right? And this is our equator plane. And this is our plus state. And this is our minus state, right? So there are other bases also like clockwise basis and anti-clockwise basis that is also there. So I'm not covering that part. So that is like to another pole in the equator. So if that is the case, now the dot product, if we can represent the dot product between this plus state and psi state, can someone tell me what is the answers? I want to see. I'll give some instant questions also. Can somebody tell me what is plus state dot inner product of plus state and psi? If psi equals to say alpha Ket 0 plus beta Ket 1, so what will be the answer of plus state dot product with psi? Just do some hand calculation and tell me the answer here. All these things will be required slowly over time. We'll derive certain things. These things will be helpful. Allowing 10-15 seconds to calculate this. Perfect. So the dot product between plus and the psi state will be alpha plus beta by square root 2, and this will be alpha minus beta by square root 2. Just I have written here, and these are exactly the gamma and delta. Because earlier your quantum state was here, Ket psi, right? So that time you were representing this information with the help of this vector and this vector, plus state, 0 state and 1 state. Now you want to represent this information using this state and this state. So hence you need to project this vector to this here and here, right? These two particular line, right? So it's a bit complicated in the blosphere, but again, like in the XYZ, if you could visualize these things. So suppose you are representing information in these two plane. Now you are representing in the say XZ plane, something like that, right? So in a different plane, how you are basically taking another two basis to represent the same informations, right? So you have to basically recalculate the probabilities, probability amplitudes, basically. So now let's see what are the things. So from here we know that both these 0, 1 as well as plus state and minus state all are basically orthonormal basis states. So this is orthonormal to this one, and this is orthonormal to this one. So you can represent quantum information either via this or via this. And our quantum state can be written as alpha plus beta by square root 2 plus state plus alpha minus beta by square root 2 minus state, right? So this is your gamma and this is your delta, right? This is your gamma and this is your delta. If I can write these things, and immediately I know, because just by inspection, that this particular part is the inner product of plus and psi state. And here I am keeping the plus state, plus minus with the psi state, inner product of these two quantum state to the minus basis with minus basis, right? I can write this way and just do some calculations. So just by interchange of the order of the product, you can always write it as equals to plus state, this way, plus state outer product with the state psi plus outer product of minus state and minus state psi. This is just a change of order of product. So then you can write your state psi as plus state outer product plus minus state and minus state outer product with the state psi. So psi state you can represent as a combination of outer product of plus state and outer product of minus state into the same state psi. It's like an evolution with the same state. And this equation will be only valid if this is equals to the identity matrix, right? So I can write always as a plus state plus minus state. This is the outer product, okay? Outer product of the, because plus and minus commute each other, they basically, I should say they are orthonormal. And hence, I can be written as plus outer product and minus outer product to validate these particular equations. And this is also equals to your 0, 0 plus 1, 1 equation. And this is called the completeness relation. Right. This one is important because when we'll be defining, say for example, we want to, instead of in fact 0, 1 or plus minus, suppose we want to design certain basis set for chemistry like H2O or various other basis sets, right? Suppose our basis sets are certain I and J, two arbitrary basis sets. What information we only know that I is orthogonal to J and for any Ij, right? And the norm of this I and J equals to 1. This is what I know. Then immediately I can create an operator. So that operator is outer product of I plus the outer product of J and J and that will be making an identity operator. So I can easily use them to represent my quantum information in that basis, right? So now, yeah, if there is any question, you are feel free to write. We can talk. Now we'll check how it helps in our reversibility of quantum operations, right? So first part, I'm keeping mostly the quantum information itself, various aspects of measurement, probabilities, and how various eigenbases and the measurement basis works, and that creates the basically help us to find out the information out of a quantum state, and we'll define various measurement operators, and slowly I will go various terminology like entropy and other things. So that will be easy for understanding once we understand the basics of the quantum information itself. Okay. So because initially we'll feel, okay, this is like a quantum computing part, but eventually we'll see all this information content will be useful in the communication. So let's start with a state 0, suppose, and I apply some quantum operator, okay, and I want to get gate 1, right? So any quantum operator, suppose I apply a X gate, poly X gate, right? It's a NOT gate, basically, NOT gate in quantum, poly X, that is basically 0, 1, 1, 0, right? I get 1. If I apply the same gate on top of it, X, I should get back 0 for all quantum logic, right? So any quantum operator U, because that's a unitary matrix, right? And even from the definition of the directly coming from the Schrodinger equation also, e to the power minus IHT, right? H is a Hamiltonian matrix, right? Hamiltonian matrix. You can easily verify that U star U equals to U star equals to the identity matrix, right? So U dagger equals to U dagger U equals to identity matrix, right? And this is also coming from this direct relationship. So if I do the overall evolution, my operator star, like it should be an unitary operator, right? So for the unitary operator, the definition is U star equals to U inverse, right? For unitary, just like decaf. And if U star equals to U, then it is called the Hermitian matrix. Okay. So star means complex conjugate, right? If some matrix complex conjugate is the same matrix, it's called the Hermitian matrix. If the inverse of a matrix is its complex conjugate, it's called the unitary matrix. Okay. Now the evolution of a closed quantum system. Gate psi is like a state is passing through a unitary matrix block, and we are getting U times the psi state, right? And later, when we'll have a probabilistic descriptions of ensembles of such states with a rho, and it will pass through an operator U, we'll see it is U dagger rho U, or U rho U dagger, something like that. We'll check what is the state, right? So before that, in the second half, I'll be defining the density matrix, and then it will be clear. Right. So still, we do not have any noise in the picture. So it's a purely noiseless quantum information theory. And so when we communicate between two places, A and B are the two places, right? And we communicate between A and B, and we send some informations from here. Suppose we communicated Kate 0 from the point A, and we are getting Kate 1 from at point B. That means there is something happened in between, right? As an error, right? So this kind of error are called the bit flip error. That means you have sent 1 and you have received 0, right? So earlier in the digital communication, you have sent like 0 to 0 with a probability P, 0 to 1 with a probability 1 minus P, some binary symmetric channel, right? Something like that. But here you have sent 0, you have got Kate 1 to Kate 0, something like that, right? So that means your information earlier, it was alpha 0 plus beta 1. Just after sending it through some quantum communication channel, you got something like alpha Kate 1 plus beta Kate 0, right? Something like that. Just a the bit is flipped, quantum bit is flipped, right? So that's why, and we can check that the poly gates, basically the X gate, you can model this communication channel as a poly X channel or the bit flip channel. So the matrix 0, 1, 1, 0, right? If you apply this X on the state 0, you can get state 1. So just by simply multiply this matrix times this 0, 0 means 1, 0, right? So basically 0 times, so it will be simply just matrix vector multiplication you check, it will be 0, 1 and the vice versa, right? And similarly, if you apply X on the state gate 1, you get state gate 0, right? So that's why X gate are called the bit flip gate for computational basis. If you represent your original information in the computational basis means this 0 and 1, get 0 and get 1. There is superposition basis like plus state and minus state, or the diagonal basis plus state and minus state, and so on. So there is Fourier basis, eigen basis, so various bases to represent your informations, right? Now, if I apply this X gate, if my information is instead of this 0, 1 basis, that means if my information is represented in the plus minus basis, gamma and delta minus in this particular two bases instead of 0 and 1, and if I apply the X gate to check whether there is a bit flip or not, right? So if I apply X to minus state, right? So, and X to plus state, can somebody tell me what is the answer here? Okay, plus state equals to your 1, 1, right? And minus state equals to 1 minus 1. So there is a normalization 1 by square root 2, 1 by square root 2. What is the answer for this and this one? Just easy verify. You know the definition of X, you know the definition of plus state and minus state. Just tell me what is the vector times the matrix. No change is not the correct answer, because partly correct. You have to say two answers, one for this and another for this. So you can easily, just by doing simple matrix vector multiplications, this is also equals to 0 plus 1 by square root 2 and 0 minus 1 by square root 2. You can easily check. And if I can check it like X on the plus state, you'll be getting plus state. And if you apply X on the minus state, you'll be getting minus of minus state. Right? This equation is not just no change. There is a much more deeper meaning. So this equation is equivalent to X equals to lambda X equations, right? Eigenvalue equation. X equals to lambda X equation. If X is your eigenvector, right? So then this X and this X are not the same X, okay? So suppose this is AU equals to lambda U equation, right? For example, U is the eigenvector. So here I can check this equation that X plus state equals to nothing with plus state. That means there is a 1, and this is the eigenvalue lambda equals to 1. Here it is minus state is minus state with the eigenvalue equals to minus 1. That means X has, the poly X operator has eigenvectors or the eigenstate plus and minus with eigenvalues plus 1 and minus 1, right? So you cannot always say that X gate is the bit flip gate or the some other gate is the phase flip gate, but with respect to which information coordinate system you are telling, that is important, right? So that's why the computational basis are the basis where you can model error as the Pauli X model, Pauli X channel model, because that is basically giving you the bit flip error. But if it is, if the original information is represented in the eigenbasis or the diagonal basis plus minus, X gate is not the proper quantum channel to represent your quantum error, right? So now, similarly, so these plus and minus state are called the eigenbasis or the eigenvectors of eigenvector of the Pauli X operator, right? Sigma X. or sometimes we call X, right? That is 0, 1, 1, 0. Right? Similarly, we can check that if you apply the Z operator on the state psi, what are the things you can get if you apply the Z operator on the state psi, right? So if it is a sorry. So if it is a plus state, that plus state, and if it is a minus state, and if it is a 0 state, and if it is a 1 state. Can somebody answer this question? So if you apply, so what is the definition of Z? Z, the definition is 1, 0, 0, minus 1. This is called the Pauli Z matrix, or the Z operator, right? So you'll check that if you apply the plus state, it will become the minus state. And if you apply Z operator on the minus state, you can easily check that it will become plus state. So in fact, Z operator is the bit flip operator for the minus basis representation. If your basis representation is a minus, right? But if you apply the Z operator on the Ket0, you'll be getting Ket0. And if you apply the Z operator on Ket1, you'll be getting minus of Ket1. That means 0 and 1, which were the computational basis representation for X operator, but they are the eigenbasis of Z operator with eigenvalues plus minus 1, right? With lambda plus minus 1, right? So now that's why you will see that in many quantum circuits, people are converting things to towards the measurement, everything on the Z operator, because if you apply anything like in the quantum mechanics postulate number 2 or 3, we have seen that if there is an operator A, if you apply on a quantum state psi, right, and you want to measure out of an quantity of your desired quantity like momentum or energy, it should follow the eigenvalue equation, and the eigenvalue is little a, and this is your eigenstate representation of the wave function. Then basically you should apply that particular operator whose eigenvalue is a, which is your desired quantity, right, from the quantum postulate 2 or 3. This is the eigenstate representation of your wave functions in order to receive the desired quantity a, right? So if you are interested to measure certain quantity and your information psi is represented in the computational basis 0, 1, right, this kind of thing. So in order to get the eigenvalues, right, so which operator shall we choose as a measurement operator? G operator, right? Because that is giving me because now 0 and 1 are naturally becoming the eigenbasis for my G operator, right? So that's why people choose it, and we'll see more why these things, right? So but eventually what it does the phase change. Now if I apply G operator on the, if my information is encoded in the 0 and the 1, so 0 doesn't change, but 1 changes to minus of 1, right? So that means there is a phase part, and phase part can get reversed, right? That's why this particular operator is called the phase flip operator. So this part I talked about the measurement part, but in general, if there is a phase error, so phase error is not there in the classical information. So classical information, you have a set of strings, say 0, 1, 0, 1. In the transmitter, in the receiver, you got 0, 1, 1, 0. So this bit and this bit are corrupted because of noise and other things. So only the bit flip is the only error in classical communication. But in quantum communication, because your information is denoted by say Ket1, Ket0, Ket0, and Ket0, but you can immediately get minus of Ket0, Ket0, and Ket1, right? So both in the bit part and also in the phase part. So this phase error is an additional error that is coming in only in the quantum information part, and that you can model using the G operator, right? Pauli G operator. Okay. And there is a Pauli X also, Pauli Y operator also. The definition is 0, minus I, and 0. And we can easily write this operator as I x times z. So which can model both the bit flip error as well the phase flip error. And that's why it's called a combined bit and phase flip operator. Okay. So and also let me introduce some more relations here, because this I am not covering these things from the computing part, but these are highly relevant in quantum error channel modeling. So that's why I am relating this part, how they will help us to model various quantum error channel, right? So tomorrow we'll see various noisy channels, and this concept will be easily applicable for Pauli X channel modeling, Pauli Y channel modeling, damping channel modeling, and all. So there is a Hadamard gate, and we already know Hadamard gate is defined as 1 by square root 2, 1, 1, 1 minus 1, right? So you can also represent Hadamard gate as plus state, 0 state, plus minus state, outer product of one state. One state, right? This is also a representation of our Hadamard gate, right? And there is more relations. H equals to Z, and H equals to X. So in places where you want some G operator for certain X basis measurement, so you can convert the Y sigma, like Pauli X operator to Z operator by this relation, right? And in places where you feel, okay, I can better model certain information with bit flip error, so I can always convert all the G operator to X basis using the Hadamard gate. So this is some relation. And in general, if you apply a Hadamard gate on top of a 0 state, you get a plus state. That means purpose of Hadamard gate is to create superposition. Because this is equals to 0 plus 1 by square root 2. Similarly, if you apply 1 on Hadamard, you will be getting minus state. 0 minus 1 square root 2, right? Then let us define the measurement operator, and we'll give a break of 5 minutes. So quickly define the measurement operator. So G operator has the diagonal representation. So G operator, how we have represented. So the matrix definition is 1, 0, 0, minus 1, right? But G operator has also a very special representation in this form. Now, if it is only plus, if this minus is only plus, that means 0, 0 plus 1, 1, then it is the representation of your identity matrix, right? Your identity matrix. That basically gives already gave us the completeness relations, right? Now, so now this is the outer product representation with 0, 0 and 1, 1 basis, and let us define this part as pi 0, because it's a outer product of two vectors, right? It's a matrix pi 0, and this particular is pi 1. In fact, when you have orthonormal bases like 0, 0, 1, 1 or II, we call them as a projection operator. Projection operator. So pi 0 and pi 1 are called the projection operators, because you are projecting, basically this operator will help you to project to 0 basis and 0, 0 orthonormal basis, and this projector will help you to project a quantum state to the 1 basis, like Ket1 basis, right? So that's why pi 0 and pi 1, and G you can write as pi 0 minus pi 1 as your operator, okay? So you can quickly check that pi 0 square, that means square of this particular operator equals to pi 0. And that is giving you the definition of the projector operator. So it projects onto the subspace spanned by the vector Ket0, right? So now applying a measurement operator, applying a measurement of G operator is equivalent to ask, is the state Ket0 or Ket1? This is the question. If I measure a G operator, it is equivalent to ask the question whether the state is Ket0 or Ket1, this quantum state. Because it's probably stick superpositions. Now I have to say whether how much is the probability belongs to 0 or 1, whether the state is 0 or 1 by doing a simple single measurement, right? So because I can represent it as a like a difference of two projector operators 0, 0 and 1, 1. So it directly gives the implications that it is equivalent to us whether the state is 0 or 1, right? And if I do this like psi pi 0 psi, so this is basically is the probability of a state, right? Is psi 0 of the state in the of a quantum state to be in the state Ket0. So that means psi in the state Ket0 times 0 psi, that is equals to alpha star alpha. We have just seen this equals to alpha square. So this is the probability of the state to stay in the state Ket0. This is the probability of the state to be in the state Ket0 equals to alpha square, right? And because I am doing the basically this expectation calculation psi pi 0 psi, right? Similarly, if I do the psi pi 1 psi, that will give me the probability of the quantum state in Ket1, that is beta square, right? So these alpha square and beta square are probability of the state psi in Ket0 and Ket1. If I do the repeated measurement, so I can get this probability, right? And we have seen that if we do the measurement of the Z operator, because they have a natural eigenbasis of 0 and 1, we can easily retrieve these alpha square and beta square, right? Right. So now, now if we have a set of measurement operators instead of this pi 0 and pi 1, suppose we have a pi I as a general set of operators. It can be POVM, like positive operator valued measurement. So that particular case, if I is a set of 0 and 1, any measurement operator set I can design. So I can always get that if the resultant is +1, so the state should be pi 0 times state psi divided by square root of psi pi 0 psi. So this is just the normalization part, this one, and this is the resultant part. That should be equals to Ket0. And if the state is -1, then my resultant state will be pi 1 Ket psi by the normalization factor psi pi 1 psi equals to Ket1. So these are the two resultant state, and we'll see the if it is like a orthonormal basis set phi I instead of Ket0 Ket1. So we have seen Ket0 Ket1 and plus state and minus state. Now we'll generalize this to any orthonormal basis sets after the break. So I'm giving a break for this recording purpose. So we'll come back in 5 minutes. Feel free to post your questions. I'll pick up.